All right. Well, let's run through this. By and large, people did really well on this. In fact, I think everybody did really well on this. In some cases, you may have gotten nickel and dimed, where there's a few points here, a few points there, and they just kind of added up, especially on part 2, the multiple choice short answer. But as far as concepts, it seems like people are in a good place with the basic concepts. So let's just run through these. If you have questions on the way, go ahead and ask them. Structure name data with those fields, level, XC, val, and numbers. So everybody knows how to do the struct statement, right? Struct data, curly bracket, semicolon, and then you list the fields. So a string named level with no predefined length. So the way you want to declare a string is char star, and then the variable name. Sometimes you can use bracket bracket with nothing inside instead of char star. Sometimes you can't. This is one case where you can't. Okay, char star you really can't go wrong with, as far as I know. I've never used bracket bracket in my 40-some years of doing C. So I don't think it's very necessary. If you know when to use it, that's fine, but you'll get a compiler error if you try to do it in here. What you really want is a pointer to a character. That's how we create strings in C. So char star level. You definitely don't want char level bracket 100 or something, because that can only hold 100 elements, 100 characters. XC is just a single character, so the only way you can do that is just char XC. And then integer val, and then array of integers numbers, and that's got to be integer variable name, and then bracket length. So that defines the structure itself. Write a variable name code to have type struct data, a statement declaring a variable name code. So there's two things that happen to variables in general. We declare them, integer x, struct data star, what are we calling it, code. Okay, those are declarations. We are declaring to the compiler what this thing is. What is code? It's a pointer to a struct data. What is I? It's an integer. Okay, that's a declaration. That's totally independent of an initialization. If we do this, we can use code anywhere that we want to struct data star, and the compiler will be happy. But at runtime, code does not have any given value yet. It's probably 0. So if we try to start using code, we'll probably get a Sig Fault. So after you declare a variable, we usually do some kind of initialization. So here we're making a block of memory using malloc that will contain a struct data, and we want to set code equal to, we want it to point to that block of memory. So, and you can do this in one statement, but I broke it into 2 pieces in 2 separate questions, but just code equals malloc. And how many bytes do we want? We don't know, so we'll just say size of struct data. And the compiler will figure out how many bytes it's using for that structure, and we'll pass that to malloc. And then initialize code with the following values. Okay, so since code is a pointer to a struct data, you got to dereference it. So the typical way would be to use code arrow. And so we want the variable level to be initialized to x17. And you got to use double quotes here, because single quotes are for characters. If you don't have quotes, then it's just some variable. If you have double quotes, it becomes a string. And the compiler sees double quotes. It finds a location in memory. It stores an x, a 1, a 7, and an all terminator starting at that location. And then this quoted string gets replaced with basically whatever that address is. So this is saying code arrow level equals the address where this string is stored. And since level is a pointer to a character, when we try to use level, we'll be looking at that string. XC equals W. That's got to be a single quote. Right, single quote says, give me a byte containing the ASCII code of that character.
It's not that the character is capital or not, it's the quotes.
It's the quotes, yeah. I think I did an uppercase here, but I didn't look at that. Yeah?
Can I use point to instead of arrow?
Use what?
Just a point. Like
a period?
Yeah.
No, because if you say code dot val, it assumes that code is a struct data. And it's not. Code is some number that tells you a location in memory. Right, so that'll at least give you a warning, but it will probably give you weird results when you run it, if it actually compiles. So the arrow says dereference the pointer and then give me the dot field. All right. And yeah, that should have been number 0 and 1 that was on the board, but
Okay.
yeah.
Yeah.
All right, so linked list question. So let me copy this over here. So we got a minus 99, we got a 24, we got a minus 23, we got a null. And we want to know what's printed when you say print LL next data and LL next data. Okay, so first thing I do when I have something like this is I try to figure out what these things are relative to each other. LL is definitely our Sentinel. So LL data has 99. LL arrow next is the contents of this field, which we know is an address, and it's the address of this block. So I'm going to write down LL arrow next on top of this. And that works for me. It may not work for you. You may have to do something slightly different, because LL arrow next is really, technically speaking, it's the contents of this location of memory, this piece of the node that I'm calling LL. But I'm always interested in what these things are referring to in memory, and what I would find at that address that's stored in here is this block. So I'm going to write down that this is LL next. And if I take its next field, that's going to give me this block. And if I take that block, which is LL next, and I look at its next field, that's going to give me this last block. So LL next, and next. So you kind of have to do that for this first question. It wants to print LL next data and LL next data. So LL next data and LL next data. Okay, LL next is this block. What's the data value? 24. And LL next data is this block. Data value is minus 99. So that print statement's going to print 24 followed by minus 99. I'm feeling fuzzy. All right, next piece. Write some C code to delete the last node of the list without any loops or conditional statements. Be sure to free that node's memory too. So we want to delete this block of memory, which means we want to take the previous block and have it point to null. That'll remove this last block from the list. So we could do something like LL next is this block. We want the next field of that, next, to be equal to null. We also want to free this block, which is LL next, 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 but we've just set LL next, next, next to null. So we can't say free LL next, 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 because that'll be trying to free null. So we actually need to free this block first. So free LL next, next, next. And then we can set LL next, next, next equal to null. This is not a problem. Now in some cases we've said free should happen after you've already used the block. But we're not using this block in order to set this equal to null. Right? To set this equal to null, we need to use LL next, next, and we need to set its next field equal to null. That's what this statement is doing. But if we get rid of this block first, if we release that to the memory pool, that's fine. Because we're not using LL next, next, next data or LL next, 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 next. Right? And if we do this first, and then we try to free this block, we're going to have a Sig Fault because we're freeing null. So there's no hard and fast set of rules for how you should write these things in C. Okay, most of the time we need to use a node and then we free it at the very end, but sometimes we need to free it first. And don't try to remember which circumstances apply to which case, right? You've got to be able to think through what it is you want to do, write some code, and then go through the code and see if that's what it actually does. And that's probably the way to deal with any code around this stuff, any of these data structures. And once you can do that, you don't have to memorize 100 special cases, right? You can figure it out if you understand with a picture what you want to have happen. Where do the arrows go, what values get changed to what, and so on and so forth. And then write code to do that. All right, so that would release the last node. Create a new node with a data value of 0. So that's just a malloc call. So struct node star new equals malloc. And again, size of struct node. Sorry, it's named data. Struct data. And then set its data value to 0, so new arrow data equals 0. I think so, isn't it?
No, there's no, it doesn't specify that struct data.
Yeah, but that's
Assume each node is a struct node. Int data struct node next. Underneath the leaf list.
oh yeah. I'm on the wrong page. Okay, so struct node. Don't think too hard. Make mistakes like I do. All right, so struct node with a value of 0. It's called new, good. Okay, and then we want to insert it between the -99 and the 24. So we've got a new node. And we want to insert it right between here and there. So we want this node, LL next, to point to new. And we want new to point where LL next was pointing. So new next equals LL next next. That makes new point to the 24, and then LL next, which is this block, have that thing's next field be equal to new. And the order is important here. If I set LL next next to be new first so that this node is pointing to new, and then I say let's have new point where this node is pointing, well this is pointing to new, new's going to point to itself. And now I've got a circle in my list and I've lost all of these nodes. So again, make a stab at the code and then go through it and see if it's doing the right thing. Now, a few people did something different, which I strongly recommend, and which I actually prefer to do myself. So they did something like this. They did something like struct node star first equals LL next. In other words, they made a temporary variable. It's a pointer. They didn't do a malloc, but they said struct node star first equals LL next. So this node is also called first. And then they said struct node middle equals first arrow next. So now they've got another struct node pointer called mid, which points to this middle node. And then maybe struct node last equals middle arrow next. And so here's a last. Right, we're not doing any mallocs. These are temporary variables. When we exit whatever function we're in, these will be reclaimed. So we're not really wasting a lot of memory. But what have I got now? I've got 4 nodes, and I've got a thing pointing to each of them, LL, first, mid, and last. And now, if someone comes along and says, hey, can you delete that last node from the list? Heck yeah. How do I do that? Mid next equals null. And you want to free the memory that was being used, free last. And I don't have to think too hard now. So it takes a few more lines, but it buys you a whole lot. And now we create a new node called new, and we want to insert it between first and mid. Well, that's pretty straightforward. First next equals new. New next equals mid. And there's your insert. Can I do those in a different order? Sure. No problem at all. I can say first I want new to point here, and now I want first to point to new. That's going to work perfectly fine too. So especially when you're writing code, you know, for your programming assignments or ODPs or whatever, right? Don't underweight the value of using extra variables to point to things, right? Don't just do it because you saw us do it in class one day or you saw something online that did that, right? But if it makes sense to you, having separate things to point to each of these can save you from saying, you know, LL arrow next, arrow next, arrow next equals blah, 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 right? Make life easier on yourself. Because your effort should be on, you know, manipulating the data structure, implementing an algorithm, coming up with an algorithm, things like that. You don't really want to get too bogged down on how many arrow next should I have here, right? Or what order do I have to do these in? So set things up to let you spend your energies where you like to spend them. All right, so traversing a list with a Sentinel and counting how many times you encounter a node containing the character X. So you're making a function count. It takes a pointer to a Sentinel. So find a way that you want to use your variables. For me, I want a variable pointing to the current node that I'm interrogating. And I'm going to see if that node's got an X in it, and if it does, I'm going to bump up a counter. And when that node is equal to null, I know that I'm done, and I want to have that node begin with the first node, the node after the Sentinel. So all of that kind of suggests start off with the node after the Sentinel. And you can make a struct node star temp if you want and use that. Or you can just reuse sent because it's basically a temporary variable. And I don't need to go back to the Sentinel. So I'll start off with sent equals sent arrow next. So this is the first data node. Or if the list is empty, it's null. So I'm going to while sent is not null. And I'm going to check the Sentinel's data value. So while sent is not null, if sent's data equals x, I'll bump up a counter. So I'll declare and initialize a counter. This is the number of x's. And then whether I do that or not, I want to move to the next node of the list. So I'm going to say sent equals sent next. And I'm going to go back and loop until sent is null. When sent is null, I know that I looked at the last node of the list. I checked to see if it was x. I bumped the counter, and then I set sent to whatever that was pointing to, which was null. So I'm done with my list. I can just return my number. And there's a count function. So different ways to do this. I could start with just my bare Sentinel, and I could say, well, Sentinel next is not null. And I could see if Sentinel next data is equal to x. Right, and I could do it like that. I could do, well, Sentinel next is not null, and I could set Sentinel to Sentinel next here, and then say if Sentinel data is x. And whatever way makes sense to you is the best. So main set of issues I saw here was possibly not skipping the Sentinel, possibly skipping over the Sentinel, but also skipping over the first data node, not checking the last data node, right, exiting your loop one step too early, checking one spot beyond the end of your list, which is a Sig Fault, so having your while loop go one iteration too many, forgetting to see if the data was equal to x, just like bumping up a counter to count the total number of nodes, forgetting to initialize your counter, that's easy to forget. What else? Forgetting to move down the list, which I did when I wrote this out last section. But mostly, you know, those are edge cases. Start up and wind down. Don't do mallocs unless you want to actually create a new node. If you're using a temporary node, you can say something like struct node star temp, and then I could say temp equals sent next. And I could use temp inside here, or current, or whatever you want to call it. But what you don't want to do is say something like temp equals malloc. Because as soon as you do that, you're creating a block, a node, and you're calling it temp. And then when I say temp equals sentinel, I'm changing temp to point to the first node in my list. And I got this poor block of memory sitting out here with nothing pointing to it. It's a memory leak. Right? So don't do malloc unless you actually really want to create a block of memory somewhere, create a new node. If you just want to point to a node, you just have to declare something to be a pointer to a node, and then you can assign it with an equal statement. All right, let's talk about queues. Queues are a whole lot simpler than I've apparently made them out to be. So let me re-address what a queue is. And let's forget about heads and tails and arrays and linked lists and circular buffers and all of that stuff. Okay, here's what a queue is. A queue is a data structure that you can do two things. You can add things to it one item at a time, or you can remove things. And when you remove things, they're removed in the same order that they got added. That's the end of definition of what a queue is. Okay, that's all there is. It's just a thing. You can add stuff, you can remove stuff. And whenever you remove, it comes out in the same order that you added. So forget about tails and heads and arrays and everything else for a moment. Okay, abstract data type. It's just this cloud, you put things in there and you can also take things out. They come out in the same order they were added. And a stack is exactly the same, except they come out in the opposite order they were added. Okay, how do we imagine a queue to work? We've got to somehow keep track of the order in which things came into the queue, right? This is a problem at the store. You've got a bunch of people who want to buy and pay for their groceries, and you can only help one at a time. You want to help them in the same order that they got to the checkout area. So what do? You put them in a line. And the order that they are in the line corresponds to the order in which they're going to be taken care of. So when we add something to a queue, we sort of picture the queue as, you know, some kind of line. And you come in on one side and you work your way up and you get to this end, and everybody sort of queues up behind whoever's in front of them. Oh, my beautiful drawing. All right, so there's this queue, right? You come in on this side and you move over to the front, and everybody else who comes into the line goes behind whoever's at the back of the line. So right now, here's the back of the line, here's the front of the line. This is the next person who's going to come out of the queue. This is the last person who came in. They're the last person who's going to be up here at the front. If someone else comes in, they're going to go in the back of the line. Okay, so when we start trying to implement this, we use these words head and tail. And it's really just the front of the line and the back of the line. So you come in, where do you go? You go in the back of the line. And you're working your way up to the front of the line. When you get to the front, you're the next person who's removed from the line. Now when we implement this with an array, we talked about two variables called head and tail, and they had very specific meanings. Head was the location in the array where we were going to store whoever was at the head of the line. And tail we kept as a place where we were going to store the next person who came into the line. Okay, that's an implementation detail. Okay, as an abstract data type, think of it like this, and the head and tail are just sort of pointing to the two ends of the line. So if there's nobody in line, there kind of is no head or tail of the line, right? If there's one person in line, they're at the head of the line and they're also at the tail of the line, right? But don't confuse that with everything we did when we wrote some pseudocode and we had if head equals tail, then the queue's empty, and if tail plus 1 mod 10 equals head, then the queue's full, and all that stuff. That's implementation detail. Okay? Abstractly, think of it more simply like this. Things go into the queue, they get laid out in a line, the head is the front of the line, the tail is the back of the line. And don't get bogged down, is the tail right here, or is it the empty spot behind that last person, or something like that, right? It's more abstract than that. It's just front of the line, back of the line. So what I was hoping for was this was going to be a really easy problem, and most people got this, but they also gave me a whole lot more. Here's an empty queue. If you insert a 20, the queue just has a 20 in it. Right? No ifs, ands, or buts about it. If you next insert a 12, the queue has a 12 and a 20 in it. The 12 is over at the head, the 12 is at the tail. 20 head, 12 tail. If you say remove, the 20 is going to be removed, and the queue again only has one thing, which is a 12. If you insert a 25, now there's a 12 at the head and a 25 at the tail, and so on. Remove, 12 comes out, you got a 25. Insert a 30, you've got a 25 and a 30. And if you were to insert, if you do a remove, the 25 goes away and you've got a 30. Bless you. If you say insert 35, now you've got a 35. If you say insert 15, now you've got a 15. All right. The whole thing I was after was just the idea that as you insert things, they stack up over here. And as you remove things, they get removed from here. And so I should have said abstract data type or something, but next time I ask you about queues, I'll have you write code, because code's less ambiguous. Okay, but does that make sense as kind of an abstract view of a queue? Right? Just think of a line. Front of the line, back of the line, that's the head and the tail. And a stack, same idea, except things come out in the opposite order from which they came in. So if you're pushing things in here, we also come out that same direction. Right, so it's the opposite sense. Okay, abstract definition of a stack. What's a stack? It's a collection of things you can push, you can pop, you can see if the stack's full, you can see if the stack's empty. That's usually it. So push, pop, yes, those are totally fine as part of an abstract stack. Is full, we said that's one of the ways that you interact with a stack, see if the stack's got any space left. If SP equals 0, return. SP is not part of the abstract notion of a stack. Okay, that's an implementation detail. If we're implementing a stack by using a linked list, there's probably no SP. Right? Probably nobody has an SP in their PA3 code so far, because the top of the stack is just the node after the Sentinel. You could call it SP, but in this case it's a pointer, right? So if SP equals 0 is making some very specific assumptions about how our stack is implemented. We're probably assuming it's an array. We're assuming we start storing at element 0 and the stack pointer points to, I don't know, the next location you're going to store maybe. So C is not part of an abstract implementation of a stack. Say again? C. All right, potential Sig fault. So integer x, y equals address x, print y. Integer x declares x to be an integer. It does not give x a value. So x is equal to random crazy number. Y equals ampersand x says, tell me where x is stored. Doesn't matter what the value is. It's going to give us the address in memory. And it has an address because when you say integer x, the compiler will figure out somewhere to store x. So y is a memory location, and now we print out the value of y as an integer. That's perfectly fine. You'll get a compile warning, but no chance of a Sig fault. Part C, x, y, and z are integers. Z equals x plus y, print z. No possibility anything can go wrong there. You'll get a crazy number because x and y are crazy numbers, and z is their sum, but you're not going to Sig fault. Part D, x is an integer. It doesn't have a particular value. Y is a pointer to an integer. It's not pointing anywhere in particular. And then we say y equals ampersand x. Now y has the address of x. Y is pointing to x. And if we print star y, we're saying, see what y is pointing to, print the value you find there. That's just a fancy way of saying print the value of x. And we don't know what's stored in x. We'll get a crazy number, but no Sig fault possibility. So item B, that's your Sig fault. So integer star x. X is a pointer to an integer. Does not have a value yet, so it's pointing somewhere crazy. Y equals star x says go to that crazy place where x is pointing, see what's stored at that location. Said y equal to that, that's when you're going to Sig fault. When you say what is x pointing to, see what's stored there. If x is a 0, it's going to try to read memory location 0, classic Sig fault. So B is not only potentially but almost certainly going to give you a Sig fault. All right, allocate enough space for an array of 125 elements of type struct big. So malloc, size of struct big. That's enough space for one struct big. Multiply by 125, that's enough space for 125 struct bigs. You can also do size of struct big bracket 125, and that seems to work. But this is nice because it could be a variable amount. I didn't say you had to do this at runtime, so some people said struct big stuff bracket 125. And technically I had to give you credit for that. But this is a compile time allocation, right? When your program gets loaded into memory to begin executing, this stuff is allocated somewhere, and stuff points to it. This happens at runtime. When you actually execute this malloc statement, that's when it creates this chunk of storage. And you can allocate a lot more memory like this than you can with this static declaration. Right, so this is basically static dynamic. We like to do dynamic when possible, unless it's really clean to do static. But you got credit either way. All right, what utility helps you detect memory leaks?
Valgrind.
Valgrind. Thank you for not saying email. What would you type to compile a program named main.c if you want to use GDB to debug it? So here's the minimal that you need. GCC, that's the compiler. -G says give me debugging information. Main.c. So that's worth full credit. Main.c -o, whatever you want to call your executable, main, program, happiness, whatever. Right? So compile, include debugging information. Here's the program I'm compiling. Call the output file main. This also works. Compile, call the output file main, include debugging, main.c. And so on. Right? That also works. So GCC has got to come first, because that's the command you're running. -G can go anywhere, main.c can go anywhere, -o main can go anywhere. But -o main have got to come together, because -o says call the thing that comes after this. That's what I want to call the output file. So don't do this. Right, this is saying call the output file -G. And there's a good chance it'll actually make the output file -G, which is a pain to remove. And then it tries to link in main, which probably doesn't exist. So that's going to give you all kinds of errors. So just make sure that the -o main is together. And the way I plan to start doing this from now on, when I talk about it, put -G first, put -o main last. I think that minimizes the chance of accidentally doing -o main.c, which wipes out your C program. But any of those will work. Alright, your directory contains a make file designed to build a single program. What command you type to build that program using the make file? Make, M-A-K-E, that's all. You can say make blah, and if there's a target for blah in your file, it'll make the program blah. But make will automatically build whatever the first recipe is, the first target. And since the make file is designed to build a single program, make is perfectly safe. So I might have crossed out if you said make blah, but I didn't take off for that. But it requires you to know what that target is called. All right, write a line of C code that allocates 10 bytes of memory and assigns a variable named pointer to point to it. PTR equals malloc 10. Right, malloc takes a number of bytes. If you say malloc 10, it allocates 10 bytes. When you say PTR equals malloc 10, it sets pointer to point to that block of 10 bytes. Two statements generally true about hashes. They improve the efficiency of storing a key data pair versus using parallel arrays. Yes, because you don't have to move things around. You simply hash your key that tells you where to store it. You might have a collision, you might have to hash a second or a third time by probing, but in general it's going to be a lot more efficient than just dealing with straight arrays. So A is definitely true. Hashes do not take less space than a pair of parallel arrays. They include parallel arrays, plus extra housekeeping, so they might actually take more space. They also improve the efficiency of deleting a key, same thing as inserting. Because you use your hash function, you know exactly where the key is to delete it. So A and C are true. Hashes can only handle keys that are null terminated. Definitely not true. Your keys can be anything as long as your hash function is able to process them. So when we use GDBM as an example of a hash in C, I added null terminators explicitly so that I could use printf to look at my keys and my data, but it wasn't necessary. So A and C are the answers there. Most appropriate data structure for handling customers in a checkout line at the store, that's got to be a queue. I think everybody got that. All right, that's the example we've been using. Having a stack in the checkout line of the store is really annoying. I won't name stores, but there's some stores where you're in line for 10 minutes, and just as you're at the front of the line, somebody comes along and says, I can help you over here, and the person way behind you who just got in line goes over to a new cashier and gets taken care of right away. That's a stack-based processing, right? The last person in is suddenly the first person being checked out, and it's kind of annoying. So queues are best for that, so 10 is B. Primary purpose of a hash function is to choose an index in which to store a key. Yeah?
Why do hashes improve the efficiency of storing keys or data?
Because if we just have parallel arrays and our arrays are sorted, we have to move things down to make space to insert something new. Right? Whereas with a hash, we take our key and we just map it to an index, and that's where we store our piece of information. So that's kind of the point of a hash, is to try to get order 1 on insert and delete and search. All right, so any questions on that? Let me run through your ODP really quickly. We got like a minute. So you're going to build a small tree basically by hand. So this is ODP 211. So we're dealing with these struct T nodes. It's a node for a binary search tree. So there's a piece of data which is an integer, and there's pointers called left and right that point to more T nodes. And you're implementing a function called small. It takes 3 numbers and it returns a pointer to a T node. So here's what small does. If I call small 20, 40, 60, it should build a tree that looks like this. It's not a binary search tree, that's okay. It's a tree whose root has the value 20, whose left child has the value 40, and whose right child has the value 60. And small should return the address of this root node. All right, so there's details here, but that's basically it, right? The root contains the value passed in the first argument, left contains the second, right contains the third, root points to the left and right nodes, everything else points to null. And how do you do this? Call malloc 3 times, make yourself 3 variables. Call them, I don't know, R, L, and right, or whatever you like. So call malloc, set row arrow data equal to 20, LE arrow data equals 40, RI arrow data equals 60, or whatever these variables are called, and then set up the pointers by hand. RO arrow left equals LE. RO arrow right equals RI. LE arrow left equals null. LE arrow right equals null, and so on and so forth. You're just cobbling together these pieces by hand, and when you're done, you've got a function you can pass in 3 numbers. It'll give you back a tree. Okay, so link that in with the test bed, assess it. You should get 10 out of 10 on each test. If you're not, write a main program, call small, hop into GDB, see what your tree looks like. Okay, make sure that this is the address of a root. You can print out what that's pointing to. It should have a data value of whatever that first number is. Left and right should be other nodes. So mess around with that. I'll be in my office until 12:30 if you have questions on that. All right, I'll see you next time.